Hi everyone, welcome to day 4, P2 rational exponents. So the other day we focused on all of the exponential rules minus the rational exponents portion. So this is our focus today. So one thing to keep in mind, rational exponents, one thing we can do is we can look at everything, and if I have a to the 1 over n, we can rewrite it in radical notation. That's like saying the nth root of a. And a to the m over n is like saying the nth root of a raised to the m power, where this guy right here is known as our index. Okay, so we're going to get right to it. Our properties still remain the same. So when we are multiplying two products together, we're still going to add those exponents. All right, we can distribute. We can split things apart. When we're dividing the quotient of powers, we're going to subtract the big exponent from the little. So we're going to quickly go through these. The only difference is now we're dealing with rational exponents or fractions. Okay, so here we go. Let's look at this first example. All right, we have x to the 2/5 over x to the 3/4. So the first thing we would want to do is get these to have common denominators. So this is like saying x to the 8/20 over x to the 15/20. So I see, well, where are there more x's? There's more in the denominator, so all we're going to do is simply subtract 15/20 minus 8/20. So we're going to have an answer of 1 over x to the 7/20. And that doesn't simplify any, so that's as good as it's going to get. If we take a look at this next example here, all right, same rules apply as of yesterday or the day before. We multiply the common terms here, right? So the numbers with the numbers, the x's with the x's. So we really have -4 times 6, and then x to the 1/3, which I'm going to get common denominators again. That's going to be 4/12 times x to the 1/4, which is going to be 3/12. Okay, and now we can multiply those numbers out front, -24, and this time we're going to add those exponents. So 4/12 plus 3/12, we're going to get 7/12, and this is going to be as good as it gets. So we'll keep going on. Let's continue on to our next example. So now I just kind of group everything that's similar. So our numbers with our numbers, our x's with our x's, our y's with our y's. All right. Now we'll take care of each of those individually, but with our variables, let's get common denominators for those exponents. So 1/6 and 3/4, that common denominator will be 12. So this will really be x to the 2/12. And then this will be x to the 9/12. For the y's, the common denominator will be 4, so instead of y to the 1/2, it's really y to the 2/4. And now we can combine everything. So I take care of those numbers. 12 divided by 16, well, they each have a 4 in common. So 12 divided by 4, we get 3. 16 divided by 4, we get 4. There are more x's in the denominator, so the x's will stay in the denominators, and now we just subtract. 9/12 minus 2/12 is 7/12. And then our y's, there's more y's in the numerator, so 2/4 minus 1/4 will get y to the 1/4 in our numerator, and that'll be our final answer. Moving on to example D. Okay, I notice that the inside is cleaned up. There's nothing to combine with these guys here. So what we can do is we can distribute that 1/3 to each of those guys inside. So it's really looking like -27 to the 1/3 times x to the 9th to the 1/3 times y to the 12th to the 1/3. We can distribute that, and now we just clean things up. So this one right here, that's really saying the cube root of -27. Now we can take the odd root of a negative and we end up with a negative. So what is the cube root of 27? That's just 3. So the cube root of negative 27 is negative 3. And now, with these guys, we just do power of a power. Okay? So power of a power. So 9 times 1/3, that'll just get us to be x to the third, 9 divided by 3. With y, 12 times 1/3, that's simply going to be y, 12 divided by 3 is 4. And here's our final answer, negative 3x cubed y to the 4th. Moving on to the final example within this portion here. This is very similar to example C, where we just need to combine our like terms, if you will. All right, so numbers with numbers, A's with A's, B's with B's, and it's all the same concept here, okay? So now our A's are the only rational exponents, so we need common denominators here. So the common denominator between 3 and 4 is going to be 12 again. So instead of A to the 2/3, we're going to have A to the 8/12. And instead of A to the 3/4, we're going to have A to the 9/12. Since our B's are integers, we don't need to clean anything up there. And now we're ready just to take on the problem. So 18 divided by 9, well, 9 goes into 18 twice. So a 2 will be in the numerator. There's more A's in the denominator, so they're going to stay there. And now we just subtract 9/12 minus 8/12. That's going to be 1/12. There's more B's in the numerator, so 3 minus 1 is just B squared. And here's our final answer with F. Our next set of examples will be dealing with radical expressions, so let's take a look. Here we're going to simplify each radical expression and we're going to combine like terms when necessary. I'll talk about a rule once we start throwing in variables. So let's just take a look at the first two examples here, which should be a good review. So the square root of 75, our index, which we talked about earlier, since it's not written in, our index is really 2. So what we're looking for is the biggest perfect square that goes into 75. Okay, so knowing your perfect squares is very important. So I'm thinking, oh, 75, the biggest perfect square that goes into it is 25. 25, excuse me. How many times does 25 go into 75? 3. So now we're taking the square root of 25, which we all know is just 5. And the square root of 3 stays. That's as good as that's going to get. And so we have our final answer of 5 root 3. The difference with part B is now our index changes. Our index is now 3, which is odd, okay? So now we're looking for the biggest perfect cube that goes into a number. Now remember what I said earlier. I said if we're taking the odd root of a negative, that's okay. We can do that. So we can pull that negative out, and then we're really left with still the cube root of 135, okay? So we're looking for our biggest perfect cubes. It's really important to know your perfect powers because it makes life a lot easier. Don't forget to write the index down with it as we go along, okay? Our index is 3. So I'm thinking, oh, we have that negative. My biggest perfect cube that goes into 135 is 27. And 27 goes into 135 5 times. So the cube root of 27 is just 3. So what we have is negative 3. And we're left with the cube root, so don't forget to write that 3, of 5. And there is our final answer. The next examples are going to throw some variables into the mix. So I want to talk about a rule really quickly, okay? So a rule that I talk about often is power divided by index, okay? So for instance, if I have the nth root, okay, of, I'm just going to say x to the m power. The way that I figure out how to simplify that is I'm going to take my power, okay, that's my power, and this is our index. And what we're going to do is we're going to take the power divided by our index, and we're going to get some number a, okay, and we're going to have a remainder of b, okay. The a becomes the power on the outside of what comes out of that radical. The b becomes the power of what remains inside. Okay, so let's take a look at this example C, all right? And this only pertains to when we have variables. So the first thing I'm looking at is the square root of 18. So we can kind of make some side notes over here. Square root of 18. Well, that's no different than before. Square root of 18 is like saying the square root of 9 times 2, okay? So square root of 9 is 3, and I know I'm going to be left with a 2 underneath, okay? But now we're going to look at the x's, okay? So I'm going to do a little side note underneath here. So x squared. Well, the power is 2. Now, what's our index when our index isn't written in? Our index is also 2, okay? So it's 2 divided by 2. So 2 goes into 2 one time with a remainder of 0. So an x to the first comes on out, okay? So x to the first power comes out, and no x's remain, okay? Now the y to the fifth. Y to the fifth. The power is 5. Our index is 2. 2 goes into 5 twice with a remainder of 1, okay? So we're going to have a y squared that comes out, this 2, and a y to the first that stays underneath, okay? Now, one thing to keep in mind, we don't necessarily need to write those powers when it's just 1. So we can simply say 3xy squared times the square root of 2y, and that will be our answer. So that's the power divided by index rule of thumb. So let's try this next example where our index is now 3, okay? So we can still break it up. The cube root of 54, okay? And so the biggest perfect cube that goes into 54 is going to be 27. So the cube root of 27, and it goes in there twice. So the cube root of 54 is really 3, and we'll be left with a cube root of 2. Now we can take on the cube root of m squared. So this is our power divided by index, 2 divided by 3. Well, 2 is smaller than 3, so 3 doesn't go into 2 at all. It goes in 0 times with a remainder of 2. So no m's come out, but that m squared stays underneath. And now we can do the same thing for the n's. So the cube root of n to the 7th. Power, 7, divided by index of 3. 3 goes into 7 twice with a remainder of 1. So an n squared will come out, and an n to the first power will stay underneath. So again, this is our power divided by index. The last example in this set deals with multiple radicals. So the key here is we need to simplify each radical individually first before we can do any combining. So if we take a look at the cube root of 32, we're looking for the biggest perfect cube that goes into it. So we'll have 2 times the cube root And hopefully you recognize 8 is the biggest perfect cube that goes into 32, and it goes in there 4 times. Don't be confused. 4 is a perfect square, not a perfect cube. Then when we simplify the cube root of 108, I want to look for the biggest perfect cube that goes into 108, and hopefully we recognize it's 27 times 4. Okay? So now we have 2 times, well, the cube root of 8 is just 2, and we're left with the cube root of 4. Minus 3, the cube root of 27 is 3, so 3 times 3, and we're left with the cube root of 4. So now what we want to do is just combine our coefficients. So 2 times 2, we get 4 cube roots of 4, minus 3 times 3, we have 9 cube roots of 4. So now what we notice is, oh, we have like terms. This is no different than saying 4x minus 9x, okay? Where instead of x, we have the cube roots of 4. So 4 cube roots of 4 minus 9 cube roots of 4, we end up with negative 5 cube roots of 4. And here's our final answer. So the key is we want to simplify radicals individually before we can combine. All right, moving on to our next example. This is just where we're going to multiply, all right? And the only difference is now we have radicals involved. So we do what we did before. When we are multiplying two binomials, we are going to FOIL. Okay, and the thing we just have to remember is how do we multiply radicals together? All right, so if we have the square root of 7 times the square root of 7, well, that just goes to 7. Square root of 7 times negative 5 is negative 5 root 7. Then these middle guys, 2 times root 7 is just positive 2 root 7. And then 2 times negative 5 is minus 10. Now we can go ahead and combine like terms. We've got root 7s here, so we can combine those middles. So 7 minus 10, we would get negative 3. And then how many root 7s do we have? Well, we have negative 5 plus 2. So that's going to give us minus 3 root 7. So here's the final answer there. Okay, so it's no different. We just have to remember to FOIL. When we see something like this next example, this is just a fancy way of saying 3 root x minus 2 times itself. 3 root x minus 2. And now it just becomes a FOILing match just like before. All right, 3 root x times 3 root x, negative 2 times negative 2. All right, negative 2 times times 3 root x, and 3 root x times negative 2. So again, it's just a FOILing. All right, so the first thing we have is going to be 3 root x times 3 root x. Well, we do the 3 times the 3, all right, so that's going to be 9. Root x times root x is just x. Then 3 root x times negative 2, that's just going to be 3 times negative 2, so minus 6 root x. Then we have negative 2 times 3 root x, so another minus 6 root x. And then minus 2 times minus 2 is plus 4. So now we can just combine like terms, and the only like terms that we'll combine are the root x's. So we end up with 9x minus 12 root x plus 4. And there's our final answer. We can't combine anything further than that. Our last example deals with rationalizing the denominator. Okay. Now, this first example you're probably more familiar with, okay, than our last one. So we can't have radicals in the denominator. So the only way around this is to multiply both the numerator and the denominator by whatever is in that denominator, since it's all by itself. Okay, we'll talk about, well, what happens if that radical is with something else. So this is called rationalizing the denominator. We're going to multiply the numerator and the denominator by the same thing. So if we were looking, well, the square root of 3 over the square root of 3, that's really just a value of 1, right? They simplify to 1, so we're not changing the value of this, this number here, okay? And now we just multiply straight across, numerator to numerator, denominator to denominator. So our numerator just stays 3x times the square root of 3, where our denominator, root 3 times root 3, is simply 3. And now I take a look and I say, oh, well, I can simplify these guys. Okay, we can pull a 3 out. I am not going to touch what's underneath that radical. This radical right here is saying, okay, you cannot touch underneath there. But we can simplify everything out front, okay? So I see 3 over 3, well, those just can simplify. That would just go to a 1 and a 1. So we get a final answer, really, of x times the square root of 3. And there lies our final answer. This last one, though, is a little different because there's more than just a radical in our denominator. There's this group right here, okay? These go together. I can't just multiply numerator and denominator by root 2 because it will not eliminate all radicals in our denominator. So what we need to do is we need to multiply by the conjugate. I wonder if any of you remember that term, okay? So if I have a plus root b, then the conjugate is simply a minus root b, okay? And we're only going to do this of the denominator. We multiply both the numerator and the denominator, but only by the conjugate of the denominator. So we're looking at this guy right here, okay? So what we're going to do is we're going to multiply the numerator and the denominator by 5 plus root 2 over 5 plus root 2. And now it just becomes foiling the numerator and foiling the denominator, okay? So foil the numerator. So we have 6 times 5, so we end up with 30. 6 times root 2 is just plus 6 root 2. Negative 3 root 2 times 5 is negative 15 root 2. And then negative 3 root 2 times root 2, well, negative 3 times 1 is negative 3. Root 2 times root 2 is just 2. So that takes care of our numerator. Our denominator, we're going to FOIL as well. So 5 minus root 2 times 5 plus root 2. So 5 times 5 is 25. 5 times root 2 is plus 5 root 2. Then negative root 2 times 5 is minus 5 root 2. And then negative root 2 times positive root 2 is just minus 2. So now we're going to combine our like terms. In our numerator, our like terms are these guys right here. And then we're also going to clean up the 3 times 2. Okay? In our denominator, you will see that the radicals will go away. So we'll be able to clean up a little bit more, okay? So our numerator is going to be 30 minus 9 root 2, and then 3 times 2, that's going to be minus 6. Our denominator, 25, the radicals cancel, minus 2, so we get 23. Now I'm not quite done. I need to still combine my like terms in my numerator, so the 30 minus 6, and we end up with 24 minus 9 root 2 all over 23. The last thing I want to do is double check. Can we simplify anything from those 3 terms? And our answer is no. So we are just going to leave our answer as is. Okay, so that kind of takes us to that little rule over here is whenever we have something in our denominator where maybe we have C over a plus root b. All right, we're going to multiply numerator and denominator by the conjugate of the denominator. So we said, okay, a plus root b, the conjugate is a minus root b. All right, so that takes us to the end. If you take a look on the next page, you will go ahead and see that power chart. It certainly helps to fill that in and know your perfect powers. If you have any questions, let me know. Have a good day.